Hi students, in this video we're going to cover higher degree polynomials and their characteristics. So I'll let you all read the definitions. I'll tell you the high points. The degree of a polynomial is going to be the term that has the highest exponent, and the leading coefficient is the number with that variable. The domain of all polynomials is negative infinity to infinity, and we'll talk more about odd, even, and neither functions in another lesson, but just those characteristics are what you should know for right now. An even degree polynomial is going to point upwards if the leading coefficient is positive, which means that when x goes to infinity or negative infinity, the f of x values are going to approach infinity. And if the graph points downwards, the f of x values are going to go to negative infinity if x goes to infinity or negative infinity. You can see that, and this is going to be relevant when we get to drawing our own graphs, that when n is larger, the graph is going to flatten at that value. We'll talk about that when we get to multiplicity. For odd degree polynomials, the graphs are going to start low and end high. All of the blue graphs are positive versions of these respective polynomials, and the black graphs are the negative ones. So this is negative x cubed. We have that would be negative x to the fifth, and this graph is negative x to the seventh. And you can see again that since in this case x equals 0 is the 0 for all of those functions, that at that 0 value, the exponent of 7 is going to make that graph flatten, and that's going to happen at any point where you have a multiplicity greater than 1. The graph is going to flatten at that value. So for odd degree polynomials, when x goes to infinity, f of x is also going to go to infinity. And when x goes to negative infinity, f of x is going to go to negative infinity. And when the leading coefficient is negative, it's just the opposite. That is down here. I'll let you, it just flips around though. When x goes to infinity, f of x is going to go to negative infinity, and so forth. The factors of a polynomial. So if x equals some number is a 0 of that polynomial, then x minus that number is a factor of that polynomial. So we know from factoring quadratics, you could factor x squared minus 2x to be x plus 2 times x minus 4. This is what we call factoring, and we get our solutions from setting the factor equal to 0. So when we're dealing with polynomials, sometimes we're given the zeros and we need to go one step backwards to get our factors. So again, if x equal a number is a polynomial, is the 0 of a polynomial, then x minus that number is the factor of that polynomial. So we're going to use that to write the factored version of a polynomial. And I will tell you that if you just multiply the x's inside the parentheses and take into consideration the power on the outside, that's how you can determine the degree of a factored polynomial. In this case, you have x times x. That's going to be x squared. So the degree is 2. So for this one, we are given 3 zeros. And so that should alone tell us that we have perhaps a cubic polynomial, but we'll see. So we're going to have f of x equals, and now we're just writing the polynomial as factors. And so that's going to be x minus negative 4 times x minus 2 times x minus 5. And of course, that simplifies to be x plus 4 times x minus 2 times x minus 5. Now, you could stop here, and you know it's cubic because you have x times x times x, which is going to be x cubed to some x cubed, and then minus a bunch of x squared, x's, and constant terms. If you wanted to multiply this out so we can review this, you would you just multiply the binomials 2 at a time. So we get x squared. So we're going to get x squared minus 2x and then plus 4x minus 8. So 4x minus 2x is going to be 2x, and 4 times negative 2 is negative 8. So we get x squared plus 2x minus 8 times x minus 5. And then this is going back to when we did multiplying functions. So we get x cubed minus 5x squared, and then plus 2x squared minus 10x, and then minus 8x plus 40. So if you simplify that, you would get x cubed minus 3x squared minus 18x plus 40. So you don't have to actually multiply that out. You can stop right here, but I'm just showing you that at the end, we do get a third degree polynomial. For the next example, we're given the graph, and we have the roots of the graph already selected. So our four roots are x equals negative 2, x equals 1, x equals 2, and x equals 4. So if we write this in factored form, we're going to have x plus 2 times x minus 1 times x minus 2 times x plus 4. The order in which you multiply these does not matter. For these higher degree polynomials, I would just leave it in factored form. So that's it. Given the zeros, we can write the polynomial. Now, there is going to be later on, we don't know if there's some value in the front that's affecting that. We're going to see that when we start writing specific versions of polynomials. So next we have the multiplicity of a root. And the multiplicity of a root is just the number of times x minus that root is a factor of the polynomial. If we go back a slide, all of these roots have a multiplicity of 1 because we only have one factor of x plus 2. We only have one factor of x minus 1. We only have one factor of x minus 2. And we only have one factor of x plus 4. But when we see something like x plus 1 times x plus 2 cubed times x plus 3 cubed, x plus 2 squared times x plus 3 cubed, that could, of course, be rewritten to be x plus 2, x plus 2, and then x plus 3, x plus 3, and x plus 3. And we can see we have 2x plus 2s and 3x plus 3s, and that's where that multiplicity comes from. The multiplicity, again, is just the number of times that factor occurs. And remember, at roots of multiplicity that are greater than 1, the graph is going to flatten a little bit at that 0. So the impact that the multiplicity has on a graph is, for roots of odd multiplicity, the graph is going to go through the x-axis. And for roots of even multiplicity, the graph is going to bounce on that axis and return in the same direction. And that's going to create a max or a minimum value, depending on where that root of even multiplicity is located. So at x equals negative 2, because the x plus 2 has a factor, has an exponent of 1, then that's going to be odd multiplicity. And we can see the graph goes through the x-axis. At x equals 0, the exact same thing is the case, that the graph goes through the x-axis. And then at x equals 2, the graph bounces off the x-axis and goes back in the same direction because of that exponent of 2. That's what even multiplicity means, bounces and returns. So the key points for polynomials, we have the x-intercepts and the y-intercepts and the maximum and the minimum. I will tell you that without calculus, it's almost impossible to do these values exactly. And when we combine the end behavior with this, we can draw a pretty accurate graph given just the zeros and the y-intercept. So the other thing that we're going to do is we should make a sign chart to determine when f of x is greater than 0 and when f of x is less than 0. So that's all the information we need to draw our graph. So we're going to draw the basic shape of x plus 1 times x minus 2 times x plus 2 squared. We're going to check that on Desmos to just see how we did. So the first thing that we need to do is identify our zeros. That is x equals -1, x equals 2, and x equals -2. And we're just going to put in E for even multiplicity, which means we know the graph should bounce and return. So first, let's make our sign chart. And on that sign chart, we're going to put -2, -1, and +2. We'll put some infinities on either side. And so if you watch the video for quadratic inequalities or polynomial inequalities, you know that on each interval, we select a value and we substitute it into the factored version, and we just keep the sign of the number because that's going to tell us if f of x is above or below the x-axis. So if I choose x equals -3, for instance, -3 plus 1 is negative, -3 minus 2 is negative, and because of the square, that last term is always going to be positive. So two negatives are going to multiply to be a positive. And I'll tell you that at roots of odd multiplicity, our sign chart is going to change signs because the graph has to go through the x-axis. So between -2 and -1 is going to be negative. And because -1 has an odd multiplicity, we're going to change sign again. And then because 2 is... Oh, I did this backwards. Excuse me. I did that exactly backwards. -2 has the root of even multiplicity, so that should still be positive. My bad. So then that's going to change our signs around a bit, but that's going to be the principle is going to be the same. Take that off. All right, so the principle is still going to be the same, though, that at roots of even multiplicity, your sign chart will not change. At roots of odd multiplicity, it will. So between -1 and 2, we're going to get negative, and between 2 and infinity, we get positive. And again, you can check. If you substitute 0 in, for instance, 0 plus 1 is positive, 0 minus 2 is negative, and you would have a positive multiplied by a negative multiplied by a positive. It's going to be a negative. Anyway, so we know when the graph should be above the x-axis and when it should be below the x-axis. And we also know our zeros. And next, all we need is our y-intercept. So f of 0 is going to be 0 plus 1 times 0 minus 2 times 0 plus 2 squared. So that is 1 times -2 times 4, which is -8. So our y-intercept is down here. Our x-intercepts are -1, -2, and +2. So maybe we zoom in a bit so we can actually draw that. So from -infinity to -1, the graph is positive, but we're going to bounce off the x-axis at -2. So from -infinity to -2, the graph is positive. We bounce off the x-axis. Then we're going to have to turn back around to go through -1, go through the y-intercept, and turn back around to go through 2. And it looks something like that. Now we'll see how we did. I'm not an artist by any stretch. So, so it's x plus 1, x minus 2, x plus 2 squared. So let's see how that looks. It is x minus 1, x minus 2, and x plus 2 squared. So you can see the graph looks something like, if we zoom in, was it X plus? Yes, X plus 1. Let me take that out, make that plus 1. So yeah, we get our graph that, again, looks pretty accurate for what we did. You can see it right here. So that's generally how we do that. To make the video shorter, you try to do this. You should get a graph that looks like, go to Desmos and type it in, but it should look like it's x times x plus 2. So x times x plus 2, and x plus 2 in this case is cubed, and we'll take out. So we're going to get an x, and the other one should have been x plus 2. Oh, x plus 2. And it's x minus 1 cubed, so x minus 1. Oh, it's going to make me take that thing out, x minus 1 and cubed. So you should get a graph that looks something like that. But I'll leave it to you to practice that so we can keep the video kind of short. All right, so next, we have to write a specific function given the roots. So the first thing you have to do is find the roots of the polynomial. 2, write the polynomial in the form like a, which is some number, and then multiply all of the factors, and then use the y-intercept or any point to find the value of a. So the first thing that we have is we have this function where we have a root of -2, root of -2, a root of 1, and the y-intercept is 5. And we know the root has an even multiplicity because it touches the axis and turns around. So I should mention that this is I took this from Delta Math and it was multiple choice, but I just took out the options. So this is a 4th degree polynomial. So we'll know that. So it's 4th degree. So we only have 2 roots, and our roots are x equals -2 and x equals 1. I don't know why I wrote a 4. So 1. So we're going to have f of x equal, and now y-intercept, I'm sorry. So y-intercept is 0, 5. So we're going to have a, that value that we're trying to solve for, then multiplied by x plus 2 squared. You know it's even multiplicity again because it bounces and returns. And the same thing for x minus 1. And we know the point 0, 5 is on the graph. So f of 0 is going to equal a times 0 plus 2 squared times 0 minus 1 squared. And whatever we get when we substitute in 0 should be 5. We should get 5. And so that's going to be 4 times 1. So 4a equals 5. And so a is going to equal 5/4. So our function is f of x equals 4/5 times x plus 2 squared times x minus 1 squared. And again, that's how you know. So when you substitute in 0, you should get 5. And all of this simplifies to be 2 squared is 4. 4 times 1 is 4. So you get 4 equals 5. A equals 5/4. And for the last example, we have g of x has the following properties. X equals 3 is a root of multiplicity 2. X equals 0 is a multiplicity of 3. And x equals -1 is a multiplicity of 2. And we know the point 1, 8 is on the graph. So g of x is a 2 plus 3 plus 2 is a 7th degree polynomial. So g of x is going to equal x minus 3 squared. I forgot our a. So x minus 3 squared times x. So if x equals 0 is your solution, x is your factor. So then times x cubed, and then times x plus 1 squared. All right, I should have rewritten, like, it's more proper to write the x squared term, the single x term in the front. And so that was x cubed, not squared. So ax cubed times x minus 3 squared times x plus 1 squared. And we know the point 1, 8 is on the graph. So that means that when you substitute in 1, you should get 8 as an output. So g of 1 is going to equal a times 1 cubed times 1 minus 3 squared times 1 plus 1 squared. And whatever, all of that should equal 8. And so if we simplify this, all right, that's going to be 1 times, let's see, negative 2 squared is 4. 2 squared is 4 again. So 4 times 4 is 16. So we get 16a equals 8. And so that's going to imply that a equals a half. And so our polynomial is g of x equals 1/2 x minus 3, 1/2 x cubed times x minus 3 squared times x plus 1 squared. All right, so that is a bit about higher degree polynomials. There's a lot more. We have odd and even and symmetry and how we find roots in general.